It is an honor and a pleasure for me to start the series of seminars on applied mathematics at our alma mater, Applied Mathematics Center, with Professor Raymond CHAN, the City University of Hong Kong. Professor CHAN is a chair professor of the Department of Mathematics and Vice President of Student Affairs at City University of Hong Kong, and co-director of the Hong Kong Center for Cerebrocardiovascular Health Engineering. He is a winner of many important prizes, among which the Feng Kang Prize, the Morningside Award, Science Fellow, and AMS Fellow, and many others. Raymond CHAN has published more than 150 journal papers and authored 3 books. He was in the ISI Science citation list of top highly cited mathematicians in the world, and was recently ranked in the top 100 in the field of numerical and computational mathematics in the Stanford 2020 study of the world's top 2% scientists. He has served on the editorial board of many journals, including Asian Journal of Mathematics, Advanced in Computational Mathematics, Journal of Mathematical Imaging and Vision, Journal of Scientific Computing, Numerical Linear Algebra with Application, Siam Journal on Imaging Science, and Siam Journal on Scientific Computing, and many others. He presented over 190 invited conference talks in more than 20 countries, including plenary talks and Siam Conference on Applied Linear Algebra and Siam Conference on Imaging Science. I think you remember the plenary talk in Bologna on Siam IS 2018. His wonderful group of graduate students include Xiaoqing Zing, the Vice President of East Asia Siam and former head of the Mathematics Department of Macau University, Michael Ng, former head of Department of Mathematics at the Hong Kong Baptist University, Director of Research at the University of Hong Kong, and Science Fellow and the Feng Kang Prize winner. Wei Qing, former head of Department of Mathematics at the University of Hong Kong, Ai Wei San, head of Department of Mathematics at the University of Macau, Ao Min Zhu, a Feng Kang Prize winner, Deng Zhan Bai, the first prize winner on Applied Numerical Algebra Prize, and Xiao Kai, the first prize winner of Asia Siam Student Prize in 2013. We are honored to have Raymond CHAN as the first speaker of this series, and I am proud to have him as a friend. Thank you very much, Raymond, and please, you can start. Thank you very much.
Okay, thank you, Fiorella, for the introduction. And well, I'm very pleased to be the first speaker in this series. And unfortunately, I cannot come in person. Otherwise, then I would very much like to join your Christmas party after this this talk. So I hope that this pandemic will be over next year, and then I can come to Italy again. I really miss Italy. Okay, so let me start the talk today. So today the talk is about sparsity. It's a kind of a introduction to sparsity. Yeah. So I don't know the background of the audience, but I presume that you are not in. Well, of course you can be in image processing, but maybe you are not. Okay, so I hope you can get something out of it. So, okay, let me see. So this is the outline of my talk. So basically, well, the goal of my talk. So basically, I would like to try to tell you that we can use the sparsity to improve the image quality. So I will talk about one example. Basically, this one. Three example, but this is one of these. For example, here is an object that observed from a telescope from the Earth, and then we can use sparsity to get something that is very clear out of it. Or you have, let's say, a low resolution video. This is a video captured by a wheel camera. Suppose I suppose you cannot see any words here. Not to mention this, okay? But after using sparsity, we can get something very clear out of it. And even these words here, so 1999 to 2000, you can easily see it now. This is all based on sparsity, and that's the goal of my talk today. So this is the outline of my talk. So I will talk about image basics, just in case you are not into image processing, and then I will talk about sparsity, how to get more from Nest. And then I will talk about, actually I will talk about three applications. Here I will talk about one MRI application, and then a ground-based astronomy application, and finally the 3D point source localization applications. So let me just use 2 minutes to talk about what is an image, just in case you are not into image processing. So if you look at this image, so this is not a black and white image. In fact, because if you zoom into the the image, then you see the pixel. And the pixels usually are numbered by, we use a number to indicate the grayness of this pixel. For example, here, if a pixel is completely white, then we give this number 255, and then if it's completely black, then we give a number 0. And then if you look at this, then this image basically is a matrix with numbers between 0 and 255. The reason for using 255 is that it's 8-bit or 1 byte for each pixel. So if you have a 1000 pixel across and a 1000 pixel down an image like this, then you require this 1 megapixel image, and then you require 1 megabyte storage. But of course, using your mobile phone now, you can easily get to 14 or 15 megapixels easily. Usually for an image, when we do image processing, we will concatenate them into column by column into a long vector. So for example, here, then 1 megapixel image will become a 1 million long vector. So for the color image, we will break it into 3 channels, red, green, and blue. For example, this one. So this is a color image, and then if you look at the red channel, it will be something like that. So then if it's completely red, like this one, then we will give it the 255. It is blue. Okay, so there's no red there, then we give it 0, something like that. So then a color image is just a 3 grayscale image. So in order to study image using a mathematical method, then we need to know, okay, what is an image mathematically. So if you look at this image here, so if you look across the x direction, the pixel in the x direction and the pixel in the y direction, and then we denote the pixel value by fxy. For this, then you see that in most part of the image, then it's very smooth, so look like a constant. But then in some part, for example, this part here, then you see a very sharp edges. Okay. And then on this part, you see a very smooth edges. Okay. So of course, in image processing, we prefer sharp edges because then we can easily identify the object. And then we do not prefer smooth edges because they are out of focus. So then in a way, so this tells us that good image are piecewise smooth functions because this is basically constant piecewise smooth with sharp jumps like this at the edges. Okay, so this is basically the you may say the assumption that we use when we derive mathematical models to do image processing. So now let me tell you, for example, how do we do denoising for image or signal. So let me use a signal because it's easier, it's 1D. So this is a noisy signal, so with some noise here. So if you break it down, then it will be the signal that you want to find plus some noise. Okay. And then in the signal, then you see that it consists of the smooth part, but it also consists of the jump. So then you can see that a noisy image or signal basically consists of two parts, the low frequency part and the high frequency part. The low frequency part will consist of this blue part, so it's slowly variating. And the jump here, which is in the signal part, so it's high frequency because it's a jump, right? So it's high frequency. But then the magnitude is usually high, because if it's a sharp edge, then the jump will be high. But the noise, you see that is also high frequency, but the magnitude are small compared to this jump here. Okay, so in image processing or signal processing, when we try to denoise, basically, so you see that there are two high frequency parts. One is in the signal, so this one, and one is in the noise. So the problem for us in denoising is how do we separate the jump from the noise, because they are both high frequency. So this is the main issue here. So in order to do that, let me just use a very simple transform that is called the Hart transform, developed like 110 years ago, to illustrate how we can separate the jump from the noise. Okay, so let me use these 8 numbers to illustrate how do we do the Hart transform. So now you just add 2 neighboring numbers together, then you get this. And let me call it S1. And then you subtract the neighboring 2 numbers, then you get this. Okay, -1, -1, 1, and 1. Now, of course, these 8 numbers, and always we cover by, if I give you this S1 and D1, right, the sum and the difference. So we know that. So given now, let's repeat this process using this for the S1. So we just sum the 2 neighboring numbers and then get the difference of 2 neighboring numbers, then we get this. Of course, we cannot get back S1 if we are given S2 and D2. Now, if we repeat this process, and then we get S3 and D3. Okay, so then this, we get basically for these 8 numbers, then we can say that the Hart transform of this 8 number is the D1, the D2, the D3, and the S3. Now, of course, these are called the Hart coefficient of these 8 numbers. I denote it by C. Now, of course, if I can given this Hart coefficient, this 8 numbers, then we can for example, from D3 S3, then we can get S2, from D2 S2, then we can get S1, and then from D1 S1, then we can get I. Okay, so this is what we call the perfect reconstruction. So if you have this 8 number, then you can get back this 8 number. Now, but the important point to note here is that after some differencing, then you finally get some 0 here. So this is what the sparsity is about. So I will explain it later. But this 0, and you may say that it may be by luck, right, that we get a 0 here. So, but in fact, it's not. So let me apply this Hart transform to an image. Now, given an image, this is an image that I took at Columbia, because CTU and Columbia has a joint bachelor degree program. So then I went there to see our CTU student graduate there. Okay, so it allowed for an image. So of course, now when you do the summation or differencing, so you have different choices. For example, the summation now you can do, for example, every 4 pixel, you add them together, then you get S1. And then for every pixel, then you can do the x direction difference. So every 2, then you get the x direction difference, or you get the y direction difference, or you get the diagonal direction difference. Now you see that most of them are black already, so that means they are either very small or close to 0, right? So this is the S1 and all the differencing. Now, if we repeat the same thing for this S1, and then we sum every 4 pixels, and then we also compute the difference of these pixels, then now you see that S1 can be decomposed into this. Now then we have the S2 and the D's and the differencing. So you see that we will have even more small entries after the second differencing. So of course, again, so by simple arithmetic, you know that if I give you this image, then you can perfectly reconstruct this image. All right, so it's easy. So this is basically what we have seen, right, from the 1D example, and this are 2D example. So we have the perfect reconstruction. We also have many 0 or close to 0 numbers after the differencing. So let me just summarize what I have just said. So the typeframe decomposition of an image, or typeframe is an extension of wavelet. So it's just basically you can consider it as a wavelet. So the typeframe transformation is something like that. So it has it's a transform with a low pass. So let me call it HL, stand for low pass. So in the previous example, this is the summation. And then it has some high pass filter. I would call it HH for high pass. So in the previous example, it will be the X direction, the Y direction, and the diagonal direction differencing. So then the low pass, and when they apply to an image, which we concatenated into a vector, so then it will take out the low frequency part of F, and the high pass will take out the high frequency part of F. Now, if an F have no noise, then this part will be the smooth part of F, and this part will be the jump of F. Okay, because I assume that it has no noise. And then if you look at all the noise there, so the noise, so if you apply the low pass to the noise, then it may be very small or zero, but in that case they are small. And then if you apply the noise, because the noise originally is small, so if you apply the high pass to it, it will be still small. So basically, this is the idea that we use to denoise an image or a signal. Okay. So let me just another thing that for typeframe is that so given an image F, now if we apply the low pass and the high pass to it, and then we multiply the transpose of it. So basically, it's the reverse the process. Then after that, we add them together. Then we get back the F again. So that means for typeframe that they will have this formula. So this operator will equal to identity. So this is what we call the perfect reconstruction formula. So for typeframe, they will have this. So we have seen that for hard wavelet, right? So but for typeframe generally, they will have this. Okay. So with these two concept, perfect reconstruction and the separation of, and the low pass and high pass. So now then we can denoise an image using this idea. So given an F, that is a keen image plus some noise, that is the observed image, noisy image F. Now given G, how do we denoise F? So the idea is that, so given G, which is a noisy image, so you first break it into the low pass and the high pass component. Okay, and then for the high pass, then we do what we call the thresholding. Thresholding is that, so we set the small value here in this vector to be 0. So this is called thresholding. Now the reason is that, so if there are noise here, that we remember that the noise and also the jumps are here. So if the noise they are high frequency, but then they are small. So if we threshold them, then they become 0. They do not exist anymore. But then if there are jumps, then we threshold them, then it will not affect them because they are big. So after that, then now we do the inverse process. We combine them, multiply it by the transpose, and then we add them back together. Because of the perfect reconstruction, then basically we get back the F without the noise. So this is the whole idea of using typeframe to do the denoising. So if I use it using the bi-orthogonal spine wavelet, which is a typeframe, and then that's what you get. Okay. Now the question is, can we get something better? Okay. So this come to our next part. So sparsity. So maybe let me summarize what we have discussed in the first part of the talk. So what is the denoising process? So the denoising process is basically you have a noisy image G, so you break into high pass and low pass, and then you have the wavelet or typeframe coefficients, and then now you do a thresholding to set to 0 these numbers here, so that are small. Okay, and then you get a threshold coefficient. Now, so this is where the sparsity come in, because this C may not have many zero, but then after the thresholding, you will have a lot of zero. So if you recall the images, the Columbia graduation images, so you see many black pixels there, but they may not be exactly 0, but then they are small. So if then after thresholding, they are exactly 0. So you introduce a lot of zeros. So this what we call this vector is sparsified from C. Okay, so this T is a sparse vector. And now then you do the inverse process, and then onto T, and then you get the denoised image. So you see that, so F, this image may not have many zero because it's a general image. It may not have many black pixels. But then before, you see that after the transform into the Typeframe domain, then you see that this vector actually has many zero. So this is, so that means that F actually lives in a low dimensional transformed space. In this space, F is actually very low dimension. So that's what I say. So this sparsity here actually can give you a much more better picture. So, but now let us use another way to look at this thresholding process, then to lead to some variational models. So this G here, so this is a noisy image, right? So if we record our process, is basically we transform it into a low pass and high pass. This is the low pass and the high pass. This is the Typeframe coefficients. Here I call the x direction derivative, and this is the y direction derivative of G, and this is the diagonal derivative of G. And what is denoising here? So denoising basically is to threshold all these numbers that are close to zero, and then we set them to zero. Okay, so this is the denoising. So basically, so thresholding is to force more zero in these three vectors. Okay. Now, in order to do that, let us introduce a notation. So this is what we call the zero norm. So zero norm of a vector is to measure the number of non-zero entries in this vector. Okay. So then, if we understand this notation and also understand the idea behind thresholding or denoising, then now we can pose our denoising process as a variational problem. So basically, you want to find an F given G, which is noisy. So you want to find an F image such that it's close to G. Okay, but then so if you look at the x derivative of F, the y derivative of F, and the diagonal derivative of F, and then if you count the number of non-zero entries in these three vectors, so their number should be minimized. So basically, that's what the thresholding is trying to do. Now, but of course, we understand that for smooth image, so this directional derivative can be computed from these two, right? So basically, then we don't need that one, so we just need these two, and then but this one is the gradient of F, right? This zero, and then so basically, what is the denoising of this noisy image is so we try to find an F such that is close to G, but then the gradient of F using the zero norm should be small. So now then, once we understand this, then now we can pose it as a variational problem. So given G, a noisy image, in order to find the denoised image F, we want to find an F such that is close to G, right? So we minimize this two norm. So this is called the data fitting term. And then the gradient of F in the zero norm should also be small, right? So this is what we call the regression term. And then we have a balancing alpha here called the regression parameter to balance these two. But unfortunately, this NP hard problem is very difficult to solve. So somehow we have to relax on this one. So the most famous relaxation is the convexification. So we convexify this norm, and then it becomes the one norm, which one can solve very fast. And this is a very famous denoising model called the ROF model. It's given back in 92. It's called the total variational denoising model. Because this is the total variational norm of what F. So now let me illustrate how good this is. So basically, you see that. So by imposing this regression, we are trying to force that to you may say that we are basically thresholding the non-zero entry of G in the high frequency. Okay. So now let me use this idea to illustrate using how we use this using this example, the MRI. In the traditional MRI, when you put a body in this, for example, measuring the brain, so basically we want to get this image F. So the MRI machine actually is measuring not the image, but the Fourier transform of this image. So basically, it is measuring the Fourier transform of f, and here are the Fourier coefficients. In order to get a clean image, then you need the more well, this Fourier coefficient you can get, the better, right? But then it takes time to get these these Fourier coefficients. And even if you get this, when you do the inverse Fourier transform, you usually get some noise. Okay, so the problem is well, how to minimize the noise, and also how to minimize the number of sample points that we need in order to get a clean image. So one way to do it is that we use what we call the parallel MRI. So we have a parallel coil here. For example, we have 4 coils around the head, and then we put the patient into the machine. So then, because we have 4 coils here, then we can afford to take, let's say, okay, 1/2 points instead of all the points. Okay, we just take 1/2 points, then we speed up the this measurement process by 1/2 of the time. Okay, but then now you get 4 images from each of the these parallel coils. And but then because the coils are situated in different locations, for example, this one is situated around here. So then you see, you see that this part is brighter, and this one is around here. Then you see that part is brighter, and similarly like this. And also because we are not taking the full K space, then you see radiation here. So the image seems wrap around. Okay, but then now, so given these 4 images, the question is, can we use some process to get back the original picture? So there are methods like this, smash, Grampa, and sense. Now, well, but how do we use sparsity to get a clean image? So in order to do that, let us look at the process. Okay, so what is the forward process for the MRI, parallel MRI? Basically, it's a clean picture here. So you put a coil here, then that's what you get. So you see, you get some, well, this brighter here, and then you also see some radiation here. So how do we get from here to here? So basically, that's the equations. So given f, then you multiply it by a sensitivity function like this, because your coil is placed around here. So so around here, then you get more information. So you have a sensitivity function for the coil I here, and then after that, then you take the Fourier transform of this image, and then P is the selection matrix, because now you don't take all the K space coefficients, you take only part of it. Then P denote which part of it you want to take, and then you take then you get the inverse Fourier transform. Then you get this image. Of course, you also have to add on some unknown noise, and that is the image that you get. Okay, this is from the I coil. Of course, you have, for example, you have 4 coils, then you have 4 such images, and if you stack all the images into one vector here, then this become a matrix M. Then that's the equation that you get. Now, given this noisy image G, now how do we get F back? So again, so now is well, using the idea previously. So then first, then because we want to find an F such that after M, then it's close to G. So then we have this data fitting term first. Okay, so if you use the total variational model, then you use this as a regularization. That's enforce sparsity into the model. And then also you can use the Typeframe that I also mentioned before. So here then the Typeframe will be something like that. So given F, after the transform, and then after some thresholding, then you want this one to be the number to be small. So you want the 0 norm of this to be small, but then you also convexify it into 1 norm. So then this is the Typeframe model. So in any case, so both of them are trying to emphasize the sparsity in the solution. Okay. So let me reiterate this. We use 12 coils here and 33 K space data. So we speed up the time by 1/3. So the white line is where we get the K space data, and the black line is where we don't get the K space data. So this is the full SOS image. So using the full K space. So to get this image. And then so we can compare. So this one is the one that you usually use on the machine. So and this one is using the TV as a vectorization, and this one is using a very special Typeframe as a vectorization. And I don't know if you can see the enhancement here. For example, this one compared to this one, which you cannot see anything. Okay, and this one is supposed to be the best one because it's the full K space. But in that case, so if you look at region 3 and region 4 and consider the contrast to noise ratio, we have some numerical results. So you see that our contrast is much higher, and and CPU time is much faster. So you see that. So emphasize on the sparsity, get us a much better result. And I should emphasize that this kind of thresholding algorithm, we are kind of the first one to develop it in this paper, the CHAN paper. We call it Csquare per set square. So it first proposed in SBIE in 2001, and then published in this paper in 2003. And then later on, there are other thresholding algorithms that come around. So if you understand the idea now, let me use this idea for two other applications that I've been using or doing recently. The first one is the ground-based astronomy. So what is ground-based astronomy? So basically, we want to observe something in space. For example, this satellite using a telescope on Earth. So this is what you usually would observe on Earth. So you don't see a very keen satellite. You see something very blurry, like this one. So the reason for this is that, because of the atmospheric turbulence. So the air is moving here. In fact, for example, so if you look at a star, which is very far away, so we know that they are twinkle, right? So when we observe on Earth. So the reason for this twinkling is precisely because of the atmospheric turbulence. The air is moving. So for a distinct star, very far away, suppose it's to be 1 point, but then when we observe it on ground-based telescope, then we see something like that, which is very spread out. And we call this image point spread function, kxy. In fact, every point on this satellite is blurred by this function. And that's why we obtain something very blurry here. Mathematically, so you can write it like this. So the satellite image is blurred by this blurring function, the point spread function, atmospheric turbulence. The operation here is the convolution, and then with some unknown noise, then you get the observed image on the telescope. Now, if the atmospheric turbulence is known, okay, then you can write G as a vector, F as a vector, N as a vector. Then K become this K convolution become a Topic block matrix, and then now you can use what I mentioned before. So you have a data fitting term here, plus some vectorization term to try to get back F. But of course, K here is unknown. So then how do we get K? So that's the problem. So if K is known, then this method, there are many papers that we did back in early 1990 to solve this problem. But if K is unknown, then we have to, the atmospheric turbulence is unknown, right? So we have to estimate them by some means. One thing is use artificial guide star. So basically, so you shoot a laser up in the atmosphere and then burn a point there. And then you try to observe how this point is spread. Then you get an estimate of this point spread function. So in fact, this laser can send up to a very high in the sky, okay, to burn a point there. And this was proposed by these two physicists, which got the 2020 Nobel Prize, partly because of this. So in fact, back, so they did it around this time, mid-90. So around this time, my collaborator, Bob Hemmons, so here, So he did use some ideas that, well, basically, so using this, you get the K, and then it become a standard deburring problem with the K known. So then he went to a Congress, U.S. Congress, and then to testify before the Congress that why the government need to invest money into basic research. And then he used this example, okay, precisely you use this as an example to tell why the government need to support this. This is the example that he gave, okay, at that time. So if you have a buried image observed on ground, then you can get something like that. Well, basically, it's still not very clear, but then you see the solar panel, and then these antennas, and something like that. But it's not very clear, right? But what at that time is much better than this one. So now the question for us is that, so can we get something even better? So this is what we did recently. So basically, if you get something from like this, now we can get something like this, much better than this one. You can see much more detail now using our idea. So basically the idea is that, so how do we get a better K? So instead of using just laser guide star, so are there anything that we can do to get a better K? So the idea is, yes, so basically what we have to do is to measure the what we call the wavefront. So the wavefront is something like that. So when the ray before they hit the Earth, they can be planar if they're from very far away. And then after they hit the atmosphere, then they become wavy. So if we can measure this deviation from planarity, so we call it phi or wavefront, then there is a formula to get the Bearing function or the Ponsberg function. So this is the formula. So if you can measure the phi, and then restrict yourself onto the aperture of the telescope, and this is the formula. So after doing this, and then get the inverse Fourier transform and absolute square, then you get the Ponsberg function. Of course, once you get the Ponsberg function, now then it becomes a standard deburring problem, and then there are many methods to do it. Okay. So the question now is how do we measure this? So then on the telescope, big telescope, they always have this what we call the wavefront sensor. So the wavefront sensor, unfortunately, cannot measure the phi directly. Otherwise, then it's done. So, but it can only measure the gradient. For example, this is the wavefront, and then it can only basically measure the x derivative or the y derivative of the gradient. Okay. Now, of course, you may say that once we have the derivative, then we can do some integration to get this back. But unfortunately, there is still one difficult issue. That is, so this is the wavefront. And then, as I said, the wavefront sensor can only measure the gradient of phi, right? The gradient of the wavefront. But then they can only measure it on a very coarse grid. For example, something like that. Yeah. So this is the wavefront, and then the wavefront gradient, and then the no resolution. So, well, in fact, this is the case. Even for this, the world very large telescope. This is a very large telescope with 8 meter diameter. So the resolution of this wavefront sensor is only 41 by 41. The reason is that we do not have enough to make a higher resolution image here. So that's why they are usually very low resolution. So then now you see that if I do an integration on this one to hopefully try to get this, it's basically impossible. So we cannot get this very accurate phi from this. Okay. So then what should we do? Then our idea is like this. So this is a low resolution wavefront gradient, and this is what we can measure. So our aim is to get the high resolution wavefront gradient, something like that. So how do we do that? So the idea is that we use a sequence of this low resolution wavefront gradient at different time steps, and then we try to get this. Okay. So basically, once we get this high resolution wavefront gradient, then now we can do the integration. Once we have this, then we plug it into the discrete in the Fourier optic formula. Then we get the Bearing function or the Ponsberg function. once we have the point spec function, then it's a standard deburring problem to deburr G to get the F back. Hopefully that F will be very clear if this K is good. So, but then how do we get a sequence of this low resolution waveform gradient measurement? So this is a low resolution waveform gradient sensor. So the idea is that we move the telescope, okay, and then if we move the telescope, then on the overlapping region, then we have more information, then we can possibly do high resolution. This is proposed in this Jeffrey and Haas paper back in 2010. Now, of course, this idea is not new in image processing. For example, here I have a video that I've shown you at the beginning. Okay, so this video has 21 frames, so it moved maybe the 21 times. The camera moved 21 times, and the resolution is very low. Okay, so if you only take out one video, for example, the first one, then you see something like that. Basically, you don't see anything. Maybe you can see a foot here or surface here, or I don't know, so you can see it. But in any case, how do we get a better image than this one? So as I said, because we have 21 image and the camera is moving, so then we can combine all these 21 images together to get, for example, this one I did using the Typeframe algorithm that I did back in 2007, and this one is 2019 using a nuclear approach, and you see that now we can get very clear images. So the basic idea is we're using some sparsity here. Okay, this Typeframe vectorization, this is a nuclear vectorization. So the idea is that so given the reference frames, and then when the video is moving, when the camera is moving, every second, every time step, we get an additional picture, and then the additional picture, if we can measure the displacement, then we will have more information. So every picture will get us one more information to make this reference frame better. So in this example, so it's we have to measure how the camera move, but in our case here, so because we move the telescope ourselves, actually the motion is determined by ourselves. So then it's a much better problem. So now let me tell you how we do that, how we can do that. So in order to understand this, so we have to know how we get from the phi to the that's the waveform to the waveform gradient measurement. So basically that's how we get it. So basically this is the true waveform gradient dx. So this one. So now because we only can see this part of the sky, so the W is the aperture. So and then R is the downsampling operator. So this one may be very high resolution, but then the measurement is only low resolution. So then we have a downsampling operator here. Okay, so this is the first one where the AI is the identity because we haven't moved the telescope. But then starting from that, then now we move the telescope. Each time we move the telescope, and then we downsample, or we check it to this aperture, and then downsample, then we get another measurement. Okay, every time we get a new measurement. So then we get this equations for the x derivative and for the y derivative, and depending on how many times we move the telescope, so here m time, so we get m measurements here. Okay, so now So now how do we get from the measurement to get back to the phi? So again, so basically you have the noise here. So now first of all, so you do a data fitting term. So this one is basically the data fitting term. And then we can add some sparsity enhancing regularization here to get this. So now let's illustrate how good this is. Here, of course, I should emphasize that we move the telescope m time. Okay, so then that's why we have this m here. So, well, in order to illustrate how good this is, so I use a true image, and then I buried it with some kernel point spec function. In fact, we also add some error in the point spec function, and then after burying, and then we also add some noise here. and then we get something like that. So this seeing condition is 50. That means the burring is very high. Okay, so very windy, you may say. And then we get the blur function image, which you basically cannot see anything, and the PSNR is very low. And because we buried with a long point-spec function, now given this one, if you load the true point-spec function, then you can deburr it, see whether you can get something back. So here we deburr this one using the true point-spec function, then we can get something like this. So you see that basically everything is back, even the very fine antenna here. But of course, in practice, we don't have the true point-spec function, right? So we need something like that to estimate it, right? So we need something to estimate the phi. After the phi, then we plug into the Fourier optic formula. Then we get the point-spec estimate the point-spec function. So let's try to see. Okay, so after we get the point-spec function, then we use the TV to deburr it. Then that's what you see. That's what we get. Okay. So you see that, so basically you also see all the things back. So here we do not assume that we know the point-spec function. So we just have this one, and then some measurement of the this point-spec this wavefront sensor together with this one. Then we can get this back. So you see that the thing is this is very close to this one. So in this example, I have only one layer of air moving, but in practice, actually, you may have a multiple layer of air moving, L layer of air moving. So then the wavefront that you have to put into the Fourier optic formula is the summation of all these wavefront from different layers. So let me illustrate this. If you have one layer of air moving, that's what you will see, and then that's what the wavefront sensor will observe. But if you have 3 layers of air moving, that's what you will see. And that's what is observed on the wavefront sensor. Okay. And then from this one, then you have to get phi 1, phi 2, phi 3, and then the summation of this phi in order to get the point-spec function. So, but then if you work out the equation, then it's still the same. So it's more complicated, but then it's still the same. So you have phi 1 up to phi L, and then the derivative, and then the motion. Because again, so you move the telescope, and then so you know this motion matrix. For each frame and at different layers. Okay, so you know that, and then we trigger onto the aperture, and then after the downsampling, then you get the what you measure on the wavefront sensor. So now with this measurement on the wavefront sensor, now you want to find phi 1 up to phi L. So of course, then you just set up the equation that there's the data fitting term, and then you add some sparsity enhancing localization. Then you can get phi 1 up to phi L. Okay. After that, then you just plug it in. Then you get the your point-spec function. But lately, we are thinking of bigger telescope. For example, this extremely large telescope by the European Union is going to build complete in 2025. It has 39-meter diameter mirror. But even on this, the world's largest telescope, the wavefront sensor measurement is the resolution is still very small. It's only 92 by 92. So our method still valid. And here they use adaptive optics, closed loop, and then so that means that they, instead of measuring the wavefront gradient, they measure the wavefront residual gradient. But our idea still works. So of course, the one thing is that so here for this big telescope, so they, of course, you don't want to move the telescope very fast. So then, but then you think about it. So here, so we get from here to here basically because of the camera is moving. But you can think about it. So we can either shrink the camera or shrink the can, right? So we can. If the camera is not moving, then we can move the can, right? So then we can still get some additional information to get this back. So basically, so in this example, that means either we move the telescope or the object moves. But our object here is the face, right? So the wavefront. The wavefront indeed is moving with time. So then, but then now, of course, if you want to use this idea, then you need to estimate the velocity of each phi. well, some people, well, there are way to measure this, either sending up a balloon to measure this or other means. So people are doing this, but here, so we were thinking that, okay, so since we have a vectorization, we have a variational model for solving phi already. So can we also assume the velocity to be unknown, and then we build it into the model together? So because the velocity for each layer, there are only two parameters, right? The speed in the x direction and the speed in the y direction. So for each layer, then there are only two parameters. So compared to phi j, that there are just a very small number of parameters. So then we can actually put them as an unknown, and then we solve it in the variational model. In fact, we have tested this ideas, and it works. We use this example to illustrate this. So we use existing 8 milliliter very large telescope, and then they have a standard testing problem for people to test. So this one has line layers. So these are the layers height from 47 meter up to 18 kilometer. And then this is how fast the air is moving. And these are the wind speed and the direction. So basically, this is the wind velocity and each layer. So now we build a model, not only to solve for phi, but also solve for these 18 numbers together with the phi. Okay, we assume they are unknown. So then finally, we get the result. So this is the low resolution phi, and this is the true phi, and this we constructed phi. So the error is very small. So this is upsample 4 times. So we publish the results in this paper. Okay. So now let me get to the final example, where we can use sparsity also. So this is what we call the 3D point source localization. So basically, we want to determine the location of point source in 3D. So why do we want to do that? So one thing is like the swarm microscopic imaging, right? So then we try to locate the points, and then combining the points, then we get the structure. So this idea is the idea behind the 2014 Nobel Prize in Chemistry. But our main application is to try to locate the space debris in space. Okay, so we try to get all these very small debris in space. So in order to understand our method, so let us try to understand, okay, so traditionally, how do we determine the 3D locations of point source let's say, in microscope? So for example, if we want to determine the XYZ location of all these 1, 2, 3, 4, 6 points here. So one way to do this using microscope is that every time we take the focus on one plane, and then we get, for example, here we get 2 points. And then we focus on the other plane and different depth, and then we get another 2 points. And then we focus on another plane, we get 1 point here. And then by combining all these planes, then we get the 3D location of all these points. So it takes a lot of images. Okay, so here you need to take a lot of image along the depth direction in order to get the location. Now the reason for this is that, so if a point is right on the focal plane, then you see the point spec function like this. So then you know that, oh, the point is on the focal plane. Then I know the depth because I know the focal thing of the focal plane. But then if a point is above the focal plane or below the focal plane at the same distance, then unfortunately the pattern are the same. Okay, the pattern are the same. So then we cannot determine whether they are above the focal plane or below the focal plane. So that's the problem. So that's why we need to take a lot of plane, need to take a lot of measurement at different length, different depth. Okay. So now the idea is that, so can we obtain the depth by defocusing? Okay. So basically we use a very small, very strange shape, rotating point spec function or rotating lens, you may say. So this rotating lens, using this rotating lens, we only need to get one picture instead of many pictures. And then from this picture, we use a mathematical inverse model to locate not only the XY location of the points, but also the depth of the points. So here then so the main thing is that we only take one picture, and then we already get the depth of the points, because the depth is encoded in these 2D pictures. But how to encode that? So basically, you can see from here. Suppose there is a point where the x origin on the focal plane. Now the point, the image of the point is not right here. So the image of the point is a little bit off. And then you also see some ring here. Now if the point is at the origin, but x unit above the focal plane, then you see that the image it looks something like that. If it is 8 meters below the focal plane, then you see something like that. So you see that the rotation or the ring rotation, the angle, actually tell you the depth of the point. So basically the information is already encoded there, the depth information. Okay. So this is the formula. So it looks complicated, but basically, if you have a point that is delta z from the focal plane, and then if you look at the image of this point, so this is the image. And then you have a theta here. The theta contains this delta z information. So basically, that means that this ring here also already contains the delta z information. Okay. And an interesting thing here, I look here because I would talk about this later, is that also this theta here also depend on the lambda, depend on the light that you use. Okay, in taking the measurement. So this lambda is the frequency of the light. So well, let me this look complicated. So let me illustrate it using a simple mathematical notation. So suppose you have 2 points here. Basically, what you observe is that these 2 points are convolved with this rotating PSF, which is mathematically is a 3D rotation, 3D convolution, and then you get these 2 rotation here for these 2 points. And then what we basically measure is the last frame, the last line of this this thing here. So we take the last line. L is the last line. Okay, that's what you observe. Okay, on the microscope, for example. And then from this one, then because the ring already encode the depth. Now what you have to do is to find the inverse problem to get back the depth and the XY location of this. Now, of course, what complicated is that usually you have some noise here to make, for example, the ring not that clear. Okay, so this is the observed image, and then now from the observed image, then you have to get back the x, this XYZ location of these points. So again, you can use sparsity to do it. Remember that. Okay, sorry. So this is the noise after taking the last slide. So this is the okay. So this is the observed one. So then now we can use something like that, right? So given this observed image, so you try to find x such that after this convolution, after taking the last slide, it should be close to this in some norm. And then this x, now we should emphasize that it should be sparse, right? Because this x is a point source, so they should be sparse. And also we put the x to be positive because they have a positive intensity. So this is the data fitting term, this is the sparsity and enforcing term. So in our paper, so we consider the Poisson noise. So we use the KL distance as a data fitting term. And also this one said this is the NP hard, so we have to relax it. So we use this relaxation. So this one, if you look at this function, basically if a go to 0, so this is a big, and then when a going to 0, then you see that basically it tends to function where when it's 0, then it's 0. When it's non-zero, then it's 1. So basically this one tends to the 0 norm, and then we use this. This is a non-convex problem. So then, but then we still are able to solve it. So So let me illustrate the result. So here we have a 15 points. We use a telescopic image. We put this here, and then we observe something like that. And then so this is what we observe. And then then you see that so basically we get the depth. So 0 is the ground truth, and plus is the estimated location. And then we see that basically we estimate everything correctly except this one, which is a little bit off. Now, but then here also this data actually is coming from this last data, this one. So because these points are in space, and then they have different material. So now if we use a different light source to measure them, then we get for example, we use 5 different light sources to measure them, then we get 5 different images. Now if we can combine all this information together again, so then now we can get even this one. Okay. So now, not only that, by combining this information, now not only that we can get a better location, the XYZ location of this point source, of this single point, but we also get the material correct. So the different color here denote different material. So we have the green, blue, purple, black, and red material here. We have 5 materials here. So we can get them not only the location, but also we get the material correctly. So I think I'm running out of my time, so it's a good time for conclusion. So basically, I've told you some application where we use the sparsity enhancing localization to enforce sparsity, and we get very good results. And there are many other applications, of course, we can use the same idea. So, but let me just emphasize one thing that I like. So this is called the single frame super resolution for video. So that means that we are given this, for example, this low resolution video. And then, so video, of course, consists of many frames. So here, so suppose I take out each frame, and then I do upsampling. For example, I upsample them by cubic interpolation. Then I get something like that. So you may see that it's a little bit better than, so let me paste it again. So this one may be a little bit better than this one. I don't know if you can see that. Yeah. This one may be better than, but then it is not very clear, right? So the difference. Yeah, but then for each frame, we can also use some Typeframe to do some interpolation for us. And this is the result. So maybe I compare these two. So for example, you see here, then it's much clearer than this one. So so this is by frame, so we do not use any time information. So, but then it's still we can get something much clearer than this one. So I think I stop here. So thank you very much. Yeah.
Thank you very much.